Onward we go here into the next unit of study. We're still going to be recruiting the element oxygen in this case, but in this case, different from we looked at in the previous unit, the oxygen atom in these functional groups, aldehydes and ketones that we're going to be looking at, all share this carbonyl group, C double bond O. Indeed, there will be 5 functional groups which have this carbonyl group. By itself, a carbonyl group is not an actual functional group. It's just a structural component of many functional groups, again, 5 of which we'll be looking at in this case. There's 4 of them here: aldehydes, ketones, carboxylic acids, amides. There's also esters, which is not included here, but these are just a representative example of functional groups which contain these carbonyls. We'll be focusing, however, on aldehydes and ketones. Now, with respect to an aldehyde, again, having a carbonyl group, it is instructive to start looking at the carbonyl itself and then think about what is flanking it on either side. Since a carbonyl takes up 2 of the 4 bonds coming off of carbon, 2 more have to be allowed emanating from it, and those will be the 2 flanking components. So if we have a carbonyl which is flanked on one side by a hydrocarbon type carbon, given as R there, and on the other side with a hydrogen, as shown here, then we definitely have what is known as an aldehyde. There's an example of an aldehyde here. This drawing is sort of a mixture between line drawing and complete bonding structure, but this is a representative aldehyde showing that hydrogen on that carbonyl carbon. Much of the time, though, we're going to be looking at aldehydes in complete line drawing, and I've brought this up before, and this carbonyl here looks sort of lopsided. It's lopsided because there is actually a hydrogen emanating from that carbon on the bottom there. It's just not shown, as we know, in line structure. So in proper line drawing, that hydrogen and bond and the carbon do not need to be drawn, but that's still a representation of an aldehyde. Sometimes an aldehyde is written in sort of a condensed structure as CHO. You won't see that too much from me, but in some cases, if you see CHO coming off the end of a stick on a line drawing, that's an aldehyde, CHO. That's the condensed version of it. So by comparison, a ketone structure here has a little bit different architecture. Here is our carbonyl structure, and on a ketone, both flanking bonds emanating from that carbonyl carbon are hydrocarbon type carbon. So when we have that sort of thing going, that is definitely diagnostic ketone structure. Couple of representative ketones. This one over on the right is drawn completely in line drawing. Notice that this bend right here, there's nothing there, but that implies a carbon atom on there. The one over on the left is sort of a mixture, mostly line structure, but I've elected to draw the carbon in here. That's a carbon there. There's some more carbon structure over here. But it just goes to show that in many cases, some of these, so we recruit in line structure, complete bonding structure, and even condensed structure when showing these things. I would caution you, looking at this, it is the one on the left. It's tempting to call this similar to the aldehyde we saw on the previous page. So if there was a hydrogen right here, we have bond H. Well, yes, that would be an aldehyde. However, that is not the case, so that there is indeed a carbon right there in line structure. So this would definitely be a ketone. So let's take a look now at the intermolecular forces, or the strength of intermolecular forces in aldehydes and ketones. Aldehydes and ketones, this is the first structure in which we're working with a carbonyl group. That's C double bond O. And I want to compare the strength of intermolecular forces with a functional group that we've looked at before, that of an ether. An ether, we said, has weak dipole-dipole forces. So they're to do with dipole forces. And if we look at this ether molecule, there is a bond dipole going from carbon towards oxygen in both cases. Two carbon-oxygen dipoles. And oxygen is more electronegative than carbon, so that would be the direction of the dipole towards carbon. But let's break this down a little. So those two bond dipoles each have an X component, which we see right here going towards each other, as well as a Y component going in this direction, which we see right here. Notice that the X components are equal and opposite, so they completely cancel out. But the Y components of that dipole are equal and additive, so that gives that dipole moment direction in this case. So we have two carbon-oxygen bond dipoles, but only a fraction of them going in that direction. So we don't have that full carbon-oxygen dipole in that upward direction like we see here. But let's now bring in the representative aldehyde or ketone. We'll show a ketone here, but they're both the same. They're both described the same. Notice now we have in this case two, again, carbon-oxygen bond dipoles going in this direction, but the entirety of the strength of both of those bond dipoles are going in one direction. It's not like over on this side with the ether where we only had the Y component of those two dipoles in that direction. Here is the full force of those carbon-oxygen dipoles in that direction. And my point here is that if we compare the forces on there, well, the intermolecular forces, or the dipole forces on an aldehyde or ketone, similarly massed, are much stronger than those for an ether. So while ethers have what are called weak dipole-dipole forces, as we know, both aldehydes and ketones, because they have a carbonyl group, have strong dipole-dipole forces. That strong dipole-dipole force is stronger than that of ethers. So if we had a number of different functional groups on molecules which are similarly massed, if the intermolecular forces between the molecules of an aldehyde or a ketone are stronger than those of an ether of similar mass, we'd expect to have a higher boiling point for the aldehyde and the ketone, and that is exactly what we see. So let's put or add aldehydes and ketones now into our series of boiling point comparisons. We're going to be using the same ones as before. Remember, we had a representative alkane, which had dispersion forces as its intermolecular force. The representative ether, which had its weak dipole-dipole force as its intermolecular force. And we had looked at an alcohol, now way over on the right, which had the strongest intermolecular force, that of hydrogen bonding. So we have in this left to right direction the strength of intermolecular forces, and that shows up in the increasing, as we go across here, boiling points of these similarly massed molecules. Well, let's bring in similarly massed aldehydes and ketones. And we find that because aldehydes and ketones both have strong dipole-dipole forces, that they have a boiling point typically greater than ethers and less than the corresponding alcohols. Here we have both of these boiling points around 50 degrees Celsius, which is less than the about 100 degrees Celsius which we see with the alcohol. Makes sense because the alcohol has the hydrogen bonding, the strongest intermolecular force, but much greater than our aldehydes and ketones, that of the ether at about 8 degrees Celsius with their weak dipole-dipole force. Now, it should be mentioned that in this particular case, we see that the aldehyde has a lower boiling point than the representative ketone. That's not always the case. Sometimes if we look at different similarly massed molecules, the ketone would have a lower boiling point and the aldehyde would have the higher boiling point, but we don't really worry about that because they can go back and forth. They're considered as one unit. So as a summary, we can always put either an aldehyde or a ketone in between ethers and alcohols with respect to their boiling points because of that strong dipole-dipole force fits right between our weak dipole-dipole force of ethers and our hydrogen bondings, which we see in alcohols. So it would not be a functional group without a deep dive into nomenclature. IUPAC, that rule-based aldehyde nomenclature. Now, when it's IUPAC, rule-based, we have a set of rules. And over on the right-hand side here, we have a representative molecule. I know I'm going to be naming this as an aldehyde because here's that aldehyde carbonyl right there. I know there's a hydrogen emanating from that carbon. It's just not shown here. We have to get used to that sort of lopsidedness of line drawing of aldehydes, but this is an aldehyde. So we're going to be naming it as such. That may seem sort of aloof thing to say, but we have to understand, what are we naming here? What functional group is it? Is it an alkene? Is it an alcohol? Is it an ether? Is it an aldehyde? We have to think of that first, and then we move forward into this very similar, as we've seen before, set of rules of IUPAC nomenclature with some special quirks just for aldehydes, as we'll show on this particular molecule. So let's start with the rules. Our first rule is very similar for all functional groups. Identify the longest continuous carbon chain containing the aldehyde carbonyl group. Well, in this case, it would be the only carbon chain. That's not always going to be the case, but in this case, it is. And that is of 7 carbon length. If this were a 7-carbon alkane, it would be heptane. But it's not. It's an aldehyde. So the rule here is we remove the E from the corresponding alkane name and replace it with the suffix al. Heptanal. Heptanal. Heptanal because it's an aldehyde. So that suffix that's at the end of it gives you an indication, like when you see al, oh, we're naming an aldehyde. So we can add that to the constellation of hints if we're ever at a loss of how we're going to name a compound. So we have heptanal. The next rule is that we're going to number the parent chain, always giving that 1 designation to the carbonyl carbon over on the right. Well, that makes it easy. We don't have to think one way or the other way. Which way are we going to name it? Sometimes we do in IUPAC nomenclature, sometimes we don't. We don't with an aldehyde because that carbonyl has to, or the carbon of the carbonyl has to have the 1 designation. So this is how we would number that all the way to 7. So having done that, we now bring in an address for any substituents. And we name and number any substituents as previously done. We see there's a chloro group there, and it is addressed at the 5 carbon. So thus, 5-chloroheptanal. Now notice that because the aldehyde carbonyl is always at the 1 carbon, we don't have to prefix heptanal with 1. Like it would not be 5-chloro-1-heptanal, because by structural definition, it must be 1 in order to be an aldehyde. That carbonyl must be at the end of that carbon chain, that parent structure. So instead of 5-chloro-1-heptanal, that's redundant. So we forget about it, and it's just 5-chloroheptanal. We'll look at a couple of examples here. So again, we could approach these either here's a structure, give me a name, or here's a name, give me a structure. Let's start with the problem over on the left. We have a structure given. Well, what is the longest continuous carbon chain. We are naming this as an aldehyde. I should mention, we've seen, okay, there's an aldehyde carbonyl. Won't always be shown like that. Sometimes I might show the H, but we have to be clear that we're naming this as an aldehyde. So the longest continuous carbon chain, we have to meander around a little bit and be a little careful, is these 8 carbons right there. If this were an 8-carbon alkane, it would be octane, but it's not. It's an aldehyde, so we remove the E from the corresponding alkane name and put in Al. Octanal. Octanal. Wonderful. Now we number this parent chain, putting that one designation at the aldehyde carbonyl carbon, and we can see how that works out. And now we've given addresses to all of the substituents in there. Notice we have a couple of methyl groups here. That would be dimethyl. And we also have a fluoro group right there. So F in fluoro comes before the M in dimethyl. Remember that. So we're going to have that fluoro given first. 5-fluoro. And we have our 2 methyl groups at the 4 and the 6 position. So after 5-fluoro, it would be 4, 6 dimethyl octanal. 5-fluoro, 4,6 dimethyl octanal. Again, notice, if you do this in the proper succession of rules, you can really almost surprise yourself. How could I come up with a name like that? It looks so complex from that seemingly complex structure. If you learn the rules, then you can move forward and do these seemingly sometimes insurmountable problems. In any event, let's take a look at the problem on the right. Now we have a name. We're going to be asked to draw a structure. Remember, those are more like following a recipe. There's not as many sort of idiosyncrasies attached to there. But the key is we always start at the end. So what we have here, DEC, D-E-C, that is 10. I'm going to draw a 10 carbon parent structure. And there it is. And look, the decanal, A-L. So this is going to be an aldehyde, a 10-carbon aldehyde. I'm going to pop an aldehyde carbonyl on one of the ends. I'll choose that one. I could choose the other one. Notice, again, I know I may be beating this to death, but if you wanted, you could put, say, a carbon there just to see, and you could put in the hydrogen if you wanted to, just to make it look more like an aldehyde, or not. In any event, I'm choosing not to do that here. But so we have our aldehyde carbonyl applied to one of the end carbons, and now I'm going to number this structure, giving the 1 designation to that aldehyde carbonyl, 1 all the way to 10, as we see right here. And now I'm just going to follow my recipe. We have a busy 2 position here. At the 2 position, we have 2 substituents, a bromo and an ethyl, 2 bromo, 2 ethyl. We can put those in there because there's still 2 spots emanating from that bend, which is a carbon, to make the rule of 4. So I'm going to pop those in there. There's 1 bromo there, bond bromo, and our ethyl group. And then over at the 6th position, I have a phenyl group. So I'm just going to put a bond and then a phenyl. And that would be done. We are done. Remember, it's much easier going from name to structure, or more straightforward. I hesitate to use the word easy, but it's much more straightforward going from name to structure than structure to name. So onward to the nomenclature of ketones. And if you remember back when we were looking at ether nomenclature, we had 2 approaches. 2 approaches. There was a ether common nomenclature and an ether IUPAC nomenclature. We used that common nomenclature when we had simple ethers. It was an easier way of naming these things. And I had told you, well, there is one more functional group that we're going to be bringing in both common nomenclature and that rule-based IUPAC nomenclature. And ketones are it. So ketones are it. You're going to notice a lot of similarities between the type of structure, or the type of functionality on the type of structure we're looking at with ethers, as well as with the ketones right now. That is by design. So we'll look at ketone common nomenclature first. And we use this with, as I said, simple ketones. Simple meaning we can easily identify, look over on the left, identify the architecture on either side of that ketone carbonyl now in the middle. All of those I can identify, propyl, methyl, phenyl, and so on. So we would move to ketone common nomenclature, very, very similar to ether common nomenclature. Just like ethers, every ketone in ketone nomenclature has 3 words in its name, with the last word always being ketone. Remember, in ether common nomenclature, the last word was always ether. In ketone nomenclature, the last word is always ketone. And the first and the second word, just like ethers, describe the carbon architecture on either side of that carbonyl now. So let's look at some of these. Look at the structure over on the left now, and I'm going to analyze that and say that is a ketone. I know it's a ketone because I have a carbonyl which is flanked on both sides by some type of hydrocarbon. So that is by diagnostic ketone structure. So on the structure over on the left, I'm going to cleave that out and say, okay, that's a ketone. It is a ketone. So I'm going to put the word ketone in the name. And what do we have on either side? Well, here we have a 3-carbon structure on one side and a 1-carbon alkyl group on the other side. So one would be a propyl, one would be a methyl. So this would be propyl methyl ketone. Do you see that similarity we had with common nomenclature of ethers? Common nomenclature of ketones is very, very similar. Propyl methyl ketone. And since this is not IUPAC based, we don't have to go alphabetically. This could be just as correctly given as methyl propyl ketone. Remember we had the same deal with ether common nomenclature. Let's look at the structure in the middle. That is again a ketone because that ketone carbonyl is flanked on either side by some type of hydrocarbon carbon. So ketone is certainly going to be in that common name. And if we look on either side of that ketone carbonyl, we see 2 phenyl groups. They're both phenols. So we could call this a couple of things. And I'm purposely making this similar to the ether common nomenclature example. We could call this diphenyl ketone, or if we like, a little weirder, but we could say phenyl-phenyl ketone if we wanted to. It's good to have options today, right? And in these common nomenclatures, frequently there's options going from structure to name. If we look over on the right-hand side, again, two-way street, let's go from name to structure. What we have here is sec-butyl isopropyl ketone. Okay, 3 words, so that would be the ketone common nomenclature. I am going to put a ketone, or draw a carbonyl, right there, C double bond O. And I'm going to put on either side the first and the second word. Sec-butyl. Well, that was one of our 4-carbon alkyl groups. There it is, a sec-butyl group. Isopropyl. Well, there it is on the other side. Easy peasy. Sec-butyl isopropyl ketone. And of course, back to the other nomenclature for ketones, IUPAC nomenclature. We would carry this out when we have identified a ketone and perhaps even identified a noticeable architecture on one side. That's a methyl group, but we're not really sure what the rest of this is. We don't have, at least at our level of play, a knowledge of what we would call that entire thing. So we have not been able to identify the architecture on either side of that ketone carbonyl. When that happens, just like ethers, we go to the IUPAC nomenclature of ketones. IUPAC ketone nomenclature is pretty straightforward. It's similar to aldehydes, it's similar to that of alcohols. It's about finding the longest continuous carbon chain and naming it as a ketone. This is definitely a ketone structure we see in front of us. And just like always in ketone or any IUPAC nomenclature, we got to find the longest continuous carbon chain. And on this structure, we would find that longest continuous carbon chain as such. There it is. 7 carbons. 7 carbons, if that were a 7-carbon alkane, it would be heptane. But it's not. We recognize that as a ketone. So thus, we're going to remove the E from the corresponding alkane name and replace it with the suffix O-N-E. Heptane becomes heptanone. That suffix, those ending letters really give us an indication of what functional group we're dealing with. Heptanone is a ketone. Remember, heptanal was an aldehyde. Heptanol is an alcohol. So this may sound dumb, me saying it, but it helps when you're sort of stuck, how am I going to name this and what kind of functional group is this? There are hints there. All right, so it is heptanone we have in there. Now notice, as always once we identify the parent chain, we have to number it. In aldehydes, it was always one direction. We knew because that aldehyde carbonyl was always the 1 carbon. Notice, in this case, a ketone carbonyl is always on an internal carbon. And that we have a possibility of a heptanone here, but I'd have a different one. What if I had my C double bond O off of this carbon or this carbon? It would be a completely different compound. It would have a different name. So thus, for numbering this, we're going to start with number the parent chain such that the carbonyl carbon of the ketone gets the lowest numerical designation. Well, look where that carbon is on this structure. It's way over here on the right. So we're going to have to start numbering this from the right because that brings the ketone carbonyl at the lowest numerical designation, that 2 position. If we numbered it the other direction, it would be the 6th position. So based on what I said before, since that ketone carbonyl can be on many of those internal carbons, we have to prefix now, in this case, that parent's name of heptanone with the number of that ketone carbonyl. So we see that carbonyl at the 2 position. So this is 2-heptanone. Notice I've augmented the name now. It's not just heptanone, it is 2-heptanone. That's important because, as I said before, what's to stop us from having a different structure at the 3 position, a 3-heptanone or a 4-heptanone? That is important. So this is a 2-heptanone. And lastly, we name and number any substituents on there using standard IUPAC protocol. Well, I see a 1-carbon methyl group right there, and that methyl group happens to be at the 5 carbon, so I'm going to bring in 5-methyl 2-heptanone as my final answer. So let's take a look at some problem approaches to ketone IUPAC nomenclature. We'll start with the structure over on the left. First thing we do is we recognize that we're going to be naming a ketone because we have that carbonyl flanked on both sides by hydrocarbon-carbon. That is going to be a ketone. Longest continuous carbon chain is these 8 carbons right here. And so if this were an 8-carbon alkane, it would be octane. But it's not. It's an 8-carbon ketone. So octane, we remove that E and we bring in O-N-E on the very end, octanone. We would then number this parent chain, giving that ketone carbonyl the lowest numerical designation. I'd hope you could see that we'd have to number, in this case, sort of from right to left, bringing in that ketone carbonyl at the 3 position. So we'll augment that octanone name. We'll prefix it with 3-octanone. Now we have some shrubbery here, a couple of substituents. There's a methyl right there, and there's a bromo right there. So we have to go alphabetically on these. B in bromo comes before M in methyl. And we see that bromo is at the 5 position. So we're going to start this with 5-bromo, and then bring in the methyl, which is at the 6th position, 6-methyl. 5-bromo, 6-methyl, 3-octanone. Very good. Let's look at the structure in the middle. Again, recognize that this is a carbonyl-containing compound, and it is a ketone because we have hydrocarbon-carbon flanking that carbonyl carbon on that structure, so it's a ketone. And the longest continuous carbon chain would be this 6-carbon chain right here, 6 carbons. And therefore, if this were a 6-carbon alkane, this would be hexane. But it's not. It is a ketone. So we're going to remove the E from the corresponding alkane name and bring in the suffix O-N-E, hexanone. Now we will number this parent chain, giving the ketone carbonyl the lowest numerical designation. It's a little tougher in this case, but if we number from right to left, that brings in the ketone carbonyl at the 3 position. If we numbered from left to right, it would bring in at the 4 position. We want the lowest number. So we see that ketone carbonyl is at the 3 position, and so we have to prefix that hexanone name with 3. 3-hexanone. And finally, we have a bunch of substituents here. There's a fluoro group and a whole bunch of methyl groups, 1-carbon methyl groups, 3 of them, in fact. So the fluoro is going to be coming first because F in fluoro comes before M in trimethyl. That's what it's going to be. And that happens to be at the 1 position, that fluoro group. So we're going to bring in 1 fluoro. And now we look at our methyls. We see 2 methyls are attached to the 4 position and 1 attached to the 5 position. So we have to bring this in as 4, 5 dash trimethyl 3-hexanone. 1 fluoro, 4, 4, 5 trimethyl 3-hexanone. Sort of a mouthful. And yes, we do have to say 4 twice in there because 2 of the methyl groups are attached to that 4 carbons. So we have to say that twice. All right, the last one is a name going to a structure. And the way we look at these is we go to the end first, the final end, and we see heptane. So I'm going to draw heptane, 7 carbons, there it is. But we also see that O-N-E on the very end. So this is a ketone, which has an internal carbonyl. So I have to number this heptanone or heptane chain. I'm going to number it from left to right. I could number it from right to left, it wouldn't matter. But notice that the 4 position here, that's where my ketone carbonyl is going to be. So I'm going to put in a ketone carbonyl. There it is, at the 4 position. Now I notice, just to finish up, at both the 3 and the 5 position, I have a couple of chloro groups. So I am going to place a chloro group at both the 3 and the 5 position, and I am going to be finished. So that finishes us off fairly quickly, going from name to structure. So let's look, we'll start looking at representative reactions involving ketones and aldehydes, many of which we've already looked at. Remember, an oxidation of a primary alcohol to an aldehyde or a secondary alcohol to a ketone. So we've already recruited aldehydes and ketones in some of our reactions. There is crossover with respect to organic reactions between units of study because we have our functional group interconversion, say an alcohol to a ketone. Well, we're sort of standing on both sides of that. But remember now, we're going to be bringing in or showcasing a new type of reaction involving aldehydes and ketones, but it goes off the beaten path of one of our sort of most sacred ideas of organic reactions. And that is the fact that, well, we always have a functional group interconversion. Alkene to an alcohol, an alkene to an alkane, an alcohol to a ketone. So we have these functional group interconversions, which up to now has been the only way we have described organic reactions. But we're going to find that there is a second way of describing an organic reaction, And that would be with respect to, rather than a functional group interconversion, would be a functional group condensation, in which two separate functional groups condense together. And what that means is they form a covalent bond between them so that they end up as one type of structure, a different one. So notice two different functional groups covalently bind together to form a third separate type of functional group. So we're going to start this off on a diagnostic reaction of aldehydes and ketones, a little bit off the beaten path to start us on functional group condensations. But as we go through the next couple of units of study, we'll see some more perhaps familiar functional group condensations of this type. So here is our first example of a condensation reaction, a condensation of two functional groups in the formation of what are called acetals and ketals. Acetals and ketals are functionalities which are different from our original 13 functional groups, but to create them, we need to condense together two of our well-known functional groups. And we'll start specifically with acetals. Acetals are derived from aldehydes, that A in there. To make an acetal, we condense an aldehyde with an alcohol. An aldehyde and an alcohol in the journey to what is called an acetal. So we're going to covalently bind these together. And always, we're going to be looking for a central carbon. And that central carbon on an aldehyde would be that carbonyl carbon right there. That's going to be the business end of our reaction. And the oxygen atom from our alcohol is going to bond to that carbonyl carbon on that original aldehyde. So let's see what would happen if that went together. These are under conditions of catalytic acid conditions. And if we get one aldehyde condensing with one alcohol, we end up with what is called a hemiacetal. What I've tried to do is use color coding here so we can see on this now one molecule where the alcohol was derived from. It doesn't have to be this particular alcohol, by the way, but that's because it's still in red, and the rest that was in black is derived from the aldehyde. So it's important to try and recognize that. We have a hemiacetal. The word acetal is in it because it's derived from an aldehyde. Hemi typically means halfway. Like a hemisphere means half of a globe. When you see the term hemi in this context, it means we're only halfway done, because we can take another molecule of alcohol under catalytic acidic conditions, and just like before, take that oxygen atom on that alcohol is going to bond to that central carbon now on the hemiacetal. So if we do that, let's see what we end up with. Well, again, color-coded, this is you can call it a full acetal, a regular old acetal, if you will, and we spit out water. So this H2O right there, well, that oxygen from water, it was originally, look over on the left now, that aldehyde carbonyl oxygen, which becomes that sort of OH oxygen in the hemiacetal, is completely taken off in the full acetal to be as water. A full acetal, really a strange looking structure if you look at it. And we'll be talking more about that structure and how to differentiate between them as we move along and on this in the next couple of slides. But what I'm going to do now is move on to the synthesis of ketals. Now, just as acetals were derived from aldehydes, ketals are derived from ketones. ketones. So a ketone and an alcohol condensing together will now move into what we are calling ketals. Now, essentially what I'm going to be doing here is cutting and pasting what you saw on the top of this slide with what you're going to be seeing on the bottom of the slide. Notice on the two structures above and below each other over on the left, the aldehyde and the ketone, I'm drawing them both suggestively because the only structural difference now between the aldehyde and the ketone is on the aldehyde we have this hydrogen. On the ketone we have another R group. As we go through this ketal process, it's going to be exactly as above. Whereas it would be exactly the same as if I took these H's on the hemiacetal and the acetal and just converted them to an R group. I'd have exactly what we have up top. Exactly. So let's do that. With this slight structural modification, a ketone condensing with an alcohol under catalytic acidic conditions gives a remember only half done, ketal now. A hemi-ketal. Very similar to what we see on the hemiacetal above. It's just that hydrogen in the hemiacetal has now become an R group, like a methyl or an ethyl or whatever, a hydrocarbon type carbon in the hemi-ketal. If I take my hemi-ketal, meaning halfway done, and condense it again with another molecule of the alcohol, under catalytic acidic conditions, I'm going to get a full ketal. Full ketal. Ketal derived from a ketone. Acetal derived from an aldehyde. And remember, just as we saw before, that spits out that water molecule, whose oxygen atom in that water molecule was, look over on the left now, was derived from that carbonyl on the ketone, which became the OH in the hemi-ketal, now becomes that water that is cast off in that final product. So, some diagnostic structure in some of these. In boxes, I have our four new structures, again, complex. We're going to be able to tease these apart. Which one is the hemi-ketal? Which one is the acetal? We're going to be able to do that just by answering a couple questions on the next slide or the slide after. But let's look at these. We have four boxes of four new structures. And we have some diagnostic connectivity in these. In a hemi-acetal or hemi-ketal, if hemi is in the name, we have this diagnostic connectivity, COCOH. Now, why am I bringing this up? Because we're going to be seeing this in some diagnostic connectivity in biochemical structures. So this is why I'm doing this. Let's see if we can trace out COCOH on the hemiacetal on the top. Well, here's COCOH. Let's look at the hemi-ketal down on the bottom. COCOH. So if I have that diagnostic connectivity, I know I have either a hemi-ketal or a hemiacetal. It has the word hemi in it. What about over on the right, acetals and ketals? They have a diagnostic connectivity as well. And that for a full acetal or full ketal, the diagnostic connectivity is COCOC. Sounds kind of it's repetitive, doesn't it? But let's see. You know, if we look on the acetal up top, there's carbon, COCOC. It does indeed. Let's look down below on the ketal, COCOC. Now, again, this may be meaningless to you, as in who cares, but we're going to be seeing these diagnostic connectivities when we start looking at specifically carbohydrates. We're going to be looking at especially hemiacetal connectivities and sugars and so on. I just wanted to show you that there is crossover between organic chemistry and biochemistry, and that crossover can be instructive when we learn these connectivities early. We can always say in a hemiacetal, well, let's trace out the COCOH, and indeed we will be doing that in a unit of study we're going to be seeing presently. Okay, as promised, let's see if we can distinguish between these. Now, I've put up just general structures of each of the four we saw before: hemiketal, hemiacetal, ketal, and acetal. They were in those boxes on the previous slide. And if we didn't have the name tags there, they kind of look pretty much the same, don't they? And if you were given one of them, obviously without the name, it's all right, what is this? Which one is this? Acetal, hemiketal, what is it? Well, we're going to be able to do that by answering just a couple of questions. Notice also that I've drawn these now a little differently. First of all, I've taken away a lot of the color coding, but we always have that central carbon in there. Those central carbons in any of these four are going to be important because we're going to be looking at what is attached to those central carbons in order to diagnose what the identity is. So, first question. If from that central carbon, is there a hydroxyl, OH, attached directly to that central carbon? Well, if we look over on the right, in some cases, sure there is. There's one there, there's one there. In a couple cases, there's not. Who cares? Well, let's take a look why. If the answer is yes, if there's an OH, hydroxyl, directly attached to that central carbon, then the word hemi is always in the name. Notice up top where we did have those, the OHs attached to that central carbon is a hemiketal and a hemiacetal. So if we look for the presence or absence of OH attached to that central carbon, we know half the answer. If there is no OH attached to that central carbon, well, the word hemi is not in the name, and that is the case with a ketal and an acetal. So that's the first thing we can ask. Is an OH directly attached to that central carbon? What else could be attached to that central carbon? Well, how about this question? Is there a hydrogen, just H, directly attached to that central carbon? Well, if yes, the word contains, the name contains the term acetal, hemiacetal or full acetal. Now notice, here we go. Well, there's a hydrogen directly connected to that central carbon. There is a hydrogen directly connected to that central carbon. They both have the word acetal in them. If there is no hydrogen attached to that central carbon, well, in these two cases, the word acetal is not contained in the name, and thus it must be ketal. So that's where we would go ultimately with that. So let's look at a potential question. Let's label each of these as either a ketal, hemiketal, acetal, or a hemiacetal. Now notice I've drawn these in complete line drawing now, making that central carbon just an X there. There's nothing there. That would be, that means there is a carbon there in complete line drawing. In previous ones, I put the C there as the carbon atom just to show that sometimes that's not always the case. So we going with full line structure, sometimes you'll see things like this. But let's look at the structure over on the left, and we see that we have an OH attached to that central carbon. That means the word hemi is in the name. We also have a hydrogen attached to that central carbon. That means the word acetal is in the name. So thus, this would indeed be a hemiacetal. Let's look at the next one. Here's my central carbon right in the center. I have neither an OH or a hydrogen. So if there's no OH, there's no hemi in it. And if there's no hydrogen, there's no acetal in it. So this just must be a regular old ketal. It's not going to be an acetal. It's not going to be a hemiketal. just a full ketal. Let's look over the next one. There's my central carbon, and I have no OH attached to it. That means there is going to be no hemi in the name. However, I do have a hydrogen attached to it. So that means the word acetal is going to be in the name. Well, indeed, acetal is a term here, not hemiacetal, acetal. Let's look at the last one. There's my central carbon. I'm going to say I see no hydrogen attached to that central carbon. So the term acetal is not in the name. But I do see an OH attached to it. So the word hemi is in the name. So this must be a hemi-ketal. Do you see what we did there? We sort of deconstructed this so that we could we break down all of the terms so that we were left with one possible answer on each. Here's another way of looking at acetals and ketals. Let's play what's in the box, shall we? What do we have here? There is a ketone. Here is an alcohol molecule. And we have catalytic acidic conditions. What are we going to be doing here? Well, we would have to recognize that since we have one box there, that is going to be one product. So this must be a condensation. Indeed, a functional group condensation between a ketone and an alcohol. We would think back and say, well, that's going to be a hemi-ketal. All of those 2 new types of structures, had that central carbon. So what I would do is I would draw a central carbon with 4 bonds emanating from it. And we would have to realize that, and this we probably do this in stages, but we'd have to recruit in all of the shown architecture here. There's a methyl group, phenyl group, and what appears to be a propyl group right here, in some manner are going to have to be connected to that. That propyl group was connected to an oxygen, but let's see. So to put that together, this would be the structure, this hemi-ketal structure. Again, here is our methyl group, here is our phenyl group from before, and here is that propyl group attached to the oxygen that we saw previously. It takes a little doing with these, but one can indeed play what's in the box with when working with acetals and ketals.